Hello, this is Chapter 6, S. Hulkman, the continuation, so this is Chapter 6, Black Holes, Part 2. I'll need to put these on. To understand how a black hole might be formed, we first need an understanding of the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen, starts to collapse in on itself due to its gravitational attraction. As it contracts, the atoms of glass collide with each other more and more frequently, and at greater and greater speeds the gas heats up. Eventually, the gas will be so hot that when the hydrogen atoms collide, they no longer bounce off each other, but instead coalesce to form helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes the star shine. This additional heat also increases the pressure of the gas until it is sufficient to balance gravitational attraction and the gas stops contracting. It is a bit like a balloon. There is a balance between the pressure of the air inside, which is trying to make the balloon expand, and the tension in the rubber, which is trying to make the balloon smaller. Stars will remain stable like this for a long time, with heat from the nuclear reactions balancing the gravitational attraction. Eventually, however, the star will run out of its hydrogen and other nuclear fuels. Paradoxically, the more fuel a star starts off with, the sooner it runs out. I've lost my place. This is because the more massive the star is, the hotter it needs to be to balance its gravitational attraction. And the hotter it is, the faster it will use up its fuel. Our sun, who art in heaven, hallowed be your name, has probably got enough fuel for another 5,000 million years or so. But more massive stars can use up their fuel in as little as 100 million years, much less than the age of the universe. When a star runs out of fuel, it starts to cool off and so to contract. What might happen to it then was first understood only at the end of the 1920s. In 1928, an Indian graduate student, Subramanian Chandrasekhar, set sail for England, studied at Cambridge with the British astronomer Sir Arthur Eddington, an expert on general relativity. In brackets, according to some accounts, a journalist told Eddington in the early 1920s that he'd heard three people in the world who understood general relativity. Eddington paused and replied, "I'm trying to think who the third person is." During his voyage from India, Chandrasekhar worked out how big a star could be and still support itself against its own gravity after it used up all its fuel. The idea was this: when the star becomes small, the matter particles get very near each other, and so according to the Pauli exclusion principle, they must have very different velocities. This makes them move away from each other, and so it tends to make the star expand. The star can therefore maintain itself at a constant radius, by a balance between the attraction, the gravity, and the repulsion that arises from the exclusion principle. Just as earlier in its life gravity was balanced by the heat.